So again, we're going to be studying infinite series for the next few days in class. And what this video is going to go through are a few examples of how we apply the so-called test for divergence. And remember, the test for divergence, it can only tell us whether a series has a chance of possibly converging. It could still diverge after all, but what this does is kind of sift a few of the series that will just diverge right off the bat that we can determine that. So let's look at a few examples of this. So let's talk about this infinite series here. And remember, what this series represents is an infinite sum. For every single n value, when n equals 1, we plug it into that function. We add to it the value of that function when n equals 2. We add to it the value when n equals 3, when n equals 4, and so on. And what we want to know right off the bat for the test for divergence is what those terms far out in the sum look like. They must look like 0 if this series has any chance of converging. So let's just apply that idea. And the way we're going to apply this is using limits, because limits are giving us a chance of how we can ask that question. What do those terms far out in that series look like? So let's apply a limit. And we take this limit and ask, what do the terms look like far out in that sum? So the limit goes towards n equals infinity. And we take our series function, 5n squared minus 2n plus 11, all over 2n squared minus 3n plus 7 in this case. And really, we need to evaluate this limit. If this limit is anything but 0, the series automatically diverges. If it's 0, though, we get to do more work. So let's see what this limit turns out to be. Well, as n goes to infinity, this numerator looks like it's going off towards infinity. And when n goes towards infinity, this denominator also looks like it's going off towards infinity. So we have this indeterminate form, which yells at us, hey, do some L'Hopital's. So let's do some L'Hopital's rule. So remember, what L'Hopital says is we get to take the derivative of the numerator and denominator separately. So the numerator's derivative gives us 10n minus 2. Derivative of the denominator separately will give us a 4n minus 3. And then we reevaluate that limit. Well, as n goes to infinity again, this numerator, 10n minus 2, as n gets larger and larger towards infinity, this also is off to the races and goes towards infinity. And we also see a similar thing happen in that denominator. 4n minus 3 as n goes to infinity will also go towards infinity. So we have another indeterminate form, which means we again get to use L'Hopital's. So let's apply L'Hopital's again. All right, so we're still taking the limit as n goes to infinity. Again, that limit is really asking ourselves, what do those terms far out in that series look like? So as n goes to infinity, by doing L'Hopital's, taking the derivative of that numerator, we just have a 10. Taking a derivative of that denominator, the 4n minus 3, we just get a 4. And we see, well, this is just some constant number. No more n's attached. So this limit equals, well, 10 over 4. So what does this mean? Well, since this limit doesn't equal 0, therefore this series is divergent. And what this actually means to us in a more practical sense is eventually, as we go further and further out in that sum, all of those terms start looking like 10 over 4. So the terms really far out in the sum all look like 10 over 4. So in a more intuitive sense, what this means is eventually as n gets larger and larger, as we keep increasing from n equals 1 to infinity, once n gets larger and larger in this infinite sum, all of a sudden it looks like we're just adding 10 over 4, plus 10 over 4, plus 10 over 4, plus 10 over 4. And eventually that is going to blow up towards infinity in the entire sum. All right, so we did one example of applying tests for divergence. We took a limit as n goes to infinity, saw that that limit comes out to a finite number that's not 0, so it's automatically divergent in this case. Let's do a couple other examples. So here's an example. Let's consider the series n equals 1 to infinity, 1 over n squared. If we apply the test for divergence, we'll again take the limit as n goes to infinity. This time of the series function, that's just a 1 over n squared. And lo and behold, what we see as n gets very, very large in that limit, this denominator, n squared, is going towards infinity, but that numerator is a finite number. So what this overall limit looks like is 0. And this is really important. Because this limit equals 0 for the test for divergence, all this says is the series passes the test for divergence. We get to do more work. We can't say anything about the series converging or diverging at this point. So the series only passes test for divergence. And the important thing I want us to note, it could still converge or diverge. It just so happens that the first test we asked of it, it passes it. So let's do another example. And this is the series from n equals 1 to infinity and 1 over n. If we apply the test for divergence, we take the limit of that series function, 1 over n. And again, we will see that as n gets very, very large, that denominator blows up towards infinity, and 1 over a very, very large number looks just like 0. And again, we see the same exact thing happen. Because this is 0, the series passes the test for divergence. But again, all this means is the series passes the test for divergence. It could still converge or it could still diverge. We get to do more work. And in class, we're actually going to see that when a series like this passes the test for divergent, it really means it could still either converge or it could diverge. In fact, one of these two series that just passes the test for divergence, one of them is convergent and one of them is divergent. And in class, we're going to go over which is which. But at this junction, we have our first test for determining convergence or divergence for a series, the so-called test for divergence. Over the next few weeks, we're going to be adding more of these series tests to our now convergent divergent series toolkit.